Hi, everybody. My name is Grainne.
And I'm Gabe.
And we run distributed ad systems for Google. And we want to talk to you today a little bit about how we like failing when nobody notices and how we do that. So we're going to share the questions we ask to build better, reliable systems ourselves. And we'll give you some actual examples using gRPC, which is Google's open source remote procedure call. Let's see if the clicker works. Woo. So these are our rules. Those are our lovely Jenga blocks on the left. Everything is secretly a stack. Sharing is caring, because nobody likes kind of having the load all by themselves. They like to spread it around. Fail early, fail often. Degrading gracefully, don't guess about that. We're going to talk a little bit more about that as well. Measure all of the things, which you'll have heard people talking about all through the last couple of days. And best effort isn't. So this is going to be the structure of our talk as well. So six parts, so you guys know what's coming up and you won't get bored. But when we say rules, we kind of more not mean rules. We kind of mean guidelines. So your mileage may vary. This is what we found has worked for us. So I'm going to introduce you to a stack that we're going to walk through today and show you some examples on. And I'll do that first part. So everything is secretly a stack. Here's the greeter. If you want to follow along, there's a link at the bottom which takes you to the gRPC open source site, which actually has these live examples on it. This is a C++ example, and it's easy to put together. So this is kind of verbatim copied. We're going to add a translator backend to this greeter, and we're going to show you how easy that is. And we're also going to talk about what we as SREs do to make it more reliable. So in order to add that translator backend, we're going to have a quick poke around protocol buffers. And protocol buffers, OK, for anyone who hasn't, don't worry about it. We're going to do it fairly fast. But if you want to go back to the sites, there's more details on a lot of this. But the first thing we're kind of going to need is a protocol buffer to know how to talk to that translator. So as you can see, this is fairly simple. This is what it kind of looks like. The little numbers along the side there are called tags. So the first part is, what are we trying to translate? We're going to have a formal, and we're going to have a rude. That's the different types you're going to look for. The message you're going to send to the translator is the translator request. So it's a string with a message, hello, and what language you want to translate it into, and what that translation should look like. The bottom part there, the service translator, so that's the gRPC. That's going to create something called a stub for us, which gRPC is going to do useful things and generate code for us in the background. It doesn't matter what language you're using. We can generate those in multiple different languages. So you send a translator request, and you get a translator reply. Looks good, right? This is normally what you see on all these little tutorial pages. This is probably what it's going to look like after it's been around a while. So the really nice thing about protocol buffers is that they're going to grow with your service and help you do the right thing. So as things change, you're more likely to see it look like this. So there's a couple of guidelines that we would say when you're using protocol buffers is never change the type of the fields, deprecate them instead, and when you stop using them, you can mark them reserved so that tag number doesn't get reused. And if you have different binaries out there using these, they won't get confused if they're using an older or newer version. So the deprecated field, we mark them true, so you'll get a warning when someone does a build on those. And where we have reserved, it's to reduce the chance of having future badness by someone using or reusing a field and doing the wrong thing with it or causing it not to work properly. So as your services change, the protocol buffers are there to help. So that's basically it. This is what it looks like, really quick. This is the kind of thing it'll look like. So just to get it in your head in context. It isn't quite all the way correct, but this is basically what it's going to look like. So that translator has multiple clients, because like we said, everything is secretly a stack. So we're the client talking to the greeter, and it's going to talk to this translator component. We could also have an email and a help system also talking to that translator. So that translator needs to be really robust, and if parts of it go down, or parts of the complicated backends inside in it from what we don't know about, but it may have, all of the email and the help systems should also stay up and stay working. So the translator has 3 different backends it also uses. Could be more. We don't know. All we know about it is that protocol buffer that we're going to be talking to. So if one of those goes bad or crashes on the backend of the translator, it should stay up and not cause anything else to go out. But I'm going to show you really quickly in a code example how to add that translator. So now you have protocol buffer. What does that look like? So you allocate a client context. That's going to be that's the object holding all the information about the RPC. Then what you're going to do is allocate the response and request to get filled in. So those are the messages from the protocol. It's that simple. Translation request, translation reply, set hello, set what language you want it in. Then you're going to hand off to that stub. That's that service RPC that we saw earlier, and invoke that to the server to call. So you're going to get back a status. You see it's color-coded, so you can see which parts of the actual diagram it's actually referring to. So you send that translation request, and then you check the status and handle a reply. So it's like, if all OK, stick in that new hello that we've been translated for, and add that and move on. So gRPC library takes care of all that communication, the marshalling, and then the on-marshalling of those requests for you. So this is our original example code, and this is the translator added in. Ta-da! Really simple, pretty straightforward. But now, how does the greeter actually decide which translator to talk to? Because you're going to have multiple greeter tasks sharing that load, and multiple translator backends to talk to.
So that's our second item. Sharing is caring. I try to teach my children, I try to teach my services. Sharing is caring is generally about load balancing. So we balance the load really carefully. And of course, that's not what we're actually doing. What we really mean is load spreading. But everybody says load balancing, so that's what we'll keep saying here as well. What we generally try to achieve is like 3 different targets. One is redundancy, that you can fail over to other backends that still work. You generally try to improve your utilization by running like a hot configuration instead of a hot and standby that you don't use at all most of the time. It will also make your capacity management easier because you can add or remove backends from your balance set. From the point of view of capacity, latency is just another dimension of capacity. To some degree, you can trade these off against each other. What we are not going to talk about is that bit, sort of how you get the traffic from the internet to your service. You basically only can do that via DNS. That is the easy part. The hard part is figuring out, given a DNS request, how many client requests are you going to get. There's a pretty complete chapter in the SRE book on that. Feel free to read up on that. We're not going to cover that. However, we said everything is a stack. So zoom in and enhance, as they say in the American police shows, and shift right. So let's talk about this bit now, where that thing on the left is what used to be in the middle. This is your front end that gets every request on the HTTP service and then decides what the actual services you're sending it to, right? Is this sort of your favicon, or is this something more interesting? First question to ask with the load balancing is, what is your balancing strategy going to be? As a rule, we say, when in doubt, use round robin. Try to avoid doubt, but when in doubt, use round robin. For those who haven't used it, you take a random initial choice of the set you have, and then just sort of first request to the first one, second to the second, third to the third, until you go round, and then just keep going. In the worst case, for some number of bad backends, it's going to fail that fracture of queries. So if 1 out of 8 backends is bad, 1/8 of queries will fail. But that's the worst that can happen. On the other hand, the round-robin algorithm is not aware of differences in query cost, or maybe your backends have different hardware and different capacity. So when in doubt, use round-robin. It is unlikely to give you great results, but it is also really unlikely to give you terrible results. A frequent alternative strategy that people like using is least loaded. We're generally not a fan. Least loaded usually just does by number of outstanding queries. Right, so you send a request, you get a new request, don't have the answer yet, send it to somebody who doesn't yet have an outstanding request. You can either have a central thing that knows how many requests are outstanding, in which case, guess what? Every front end will hit that back end with the next query, so you get the thundering herd effect. If you don't have a central coordinator, then the clients are independent, and your least loaded is completely irrelevant to the actual load on the back end. So that has quite terrible failure modes, in particular because serving errors is, and it should be, really fast and cheap. So the backend that is failing usually has no requests outstanding, and you're going to send everything there. So the failure mode of that one is particularly bad. What we use internally. What we, well, I say recommend, but what we carefully recommend is a weighted round robin, where you don't just use the query count, you have some notion of query cost and say, this is an expensive query to a relatively underpowered backend, so I'll weight this much. That gives great results as long as everything plays along. You have a good metric for cost. So it works really great if it works, and if that fails, it fails just as badly as least loaded or POSIX errors. So when in doubt, use round robin. Let's talk about the next layer. The slide had it. Round robin is easy to reason about. Unfortunately, it has a failure mode for humans. So you establish all of these connections ahead of time, from every front end to every backend. You want to do it ahead of time because when you get the request, you don't want to spend time setting up the connection, checking if it's there. That has the downside that, of course, there's some amount of overhead and CPU and memory and network, maybe TCP, KPI Live, or whatever it is minimally. That adds up if you have a lot of backends. And the biggest downside of the everything to everything is if you have a query of death. If you have one front end that is misbehaving somehow and sending queries that your backend can't handle, that causes your backend to crash. That will, one after the other, crash every single backend. So that's great. What we suggest, if you can, if you have a lot of backends, and maybe not every front end needs every backend, is using subsets of the backends. So here's a subsetting strategy. This one is probably not great. The grouping of the backends on the right-hand side, it implies some kind of shared failure domain. So maybe they're all on the same switch or in the same rack under the same leak in the roof or whatever it is. They're using the same power supply. So you've got one thing that will take out all of the backends for an entire set of front ends. That looks different. It's actually the same. You have like front end 4 always goes to back end 4 of each of the sets. You might avoid some shared failure domains, but you still have the shared failure that if one of those clients takes down all of its backends, all of the other front ends are still impacted. It's better than the everything to everything. You're only using, in this example, a quarter of your front ends, healthy backends. But it's more than the 1/12 that you should be losing. So we distribute randomly instead. This is what my shell's $random did. So now I have 3 backends that have 1 incoming connection and 1 backend that has 6 incoming connections, and that's probably not what you wanted either. So what we prefer instead is this one. I have nothing to highlight here because now every front end has 3 outbound connections, every backend has 3 inbound connections. That's exactly what we want. It's still shuffled, it's still random. What we use is the fact that a pseudo-random number generator is actually pseudo. So each group of those use the same seed to randomize the order, so that each group has the same set. And then within that, we use our first strategy of saying, well, server 1 gets the first quarter, server 2 gets the second quarter, and so on. Gives you an evenly distribution, spread load, works great. So,
handing back over now. So now we have the greeter, and it has a translator backend, and it can find the translator backend probably using round robin, maybe using waiting round robin, but it has some ways of sharing that load across all those backends. There's a lot of different services using the translator, and we want that to be reliable. But how reliable is this now? And one of the odd things about making things reliable is the first answer to making it reliable is actually to fail early, which sounds counterintuitive, but let's have a walk through that and talk about it. So we now have our example that we've had from before with the greeter, the translator, and the backends. We should talk about deadlines. So this is how we're going to know how long we're willing to wait. How long are we willing to wait for the RPC to get back? If we don't have an answer to that question, we should be thinking about it and start to figure out what that is. Obviously, it should be fast, but how fast? So what's the end-to-end latency of that whole system? And like we said before, we might only know about the translator front ends. The translator service that's being provided to us might be adding more backends or doing more things. What's the end-to-end latency of the whole system? It should be how long we're waiting for that translator to come back to us. So typically, it's going to be higher than your SLO. You should have an SLO. and lower than the client timeout for how long that client's waiting, or having an expectation of how long it's going to wait for you to come back with the greeting. So even if it's a rough calculation, sort of a rough rule of thumb, you should be able to put numbers on these and be able to figure them out. You can look at one of the SRE book chapters called Embracing Risk, which goes through more of this in more detail. Which RPCs are serial and which ones can be made in parallel. So for that translator front end, it's probably going to call out to all three of those backends, depending on what kind of requests it's gotten to get an answer. But if you're the greeter, you just have one backend. So you'll have to do that and then wait to get an answer back. Is it useful to wait for a backend response? So if I'm a translator and maybe I have to call out to Google Cloud to get a translation, that might take a long time. So maybe I'm willing to wait extra long for that to come back, but I might already have responded back to the greeter with a response. But I might cache that result or in some way hold on to it so that if I'm having to do something that's expensive and takes a long time, I have some sort of backup if that continues to take a long time or be expensive. So the kind of TLDR of this one is that engineers need to understand the service to make an informed decision. So you need in some way, you don't need to understand everything that's inside that translator box, but you need to be able to have appreciation of what's going on with the service and how it might fit together. So where are the deadlines set? So for gRPC, let's walk through that as an example. The greeter creates a client context. And at that point, you're going to set the deadline. And you're going to set an explicit deadline. This is what that looks like. So the greeter context again, so all that object information about the RPC. We take the time now, we add a deadline to it, and then we set that as a deadline. Do you notice the way I decided to set the deadline was to use a flag to do that? And the reason I did that is because everybody knows how long it takes to do a build of a binary, to cherry pick something into it, to release it, and particularly if you're global, it's going to take a long time. If something goes wrong, and I say, actually, that new translator front end that I'm talking to has a regression that's taking way longer than normal, I actually want some way to be able to make my service robust, take a mitigation step, and do that quickly. So I'm going to set that with a flag instead. So very quickly, I can say, wait an extra 100 milliseconds for that to come back. The other thing I'm going to do is set wait for ready. What's wait for ready? The one thing about this is, for the greeter should be able to do something useful even if the translator front end goes down. So say the translator front end goes down globally, what do I do? Built into the greeter code in the original slide that you saw is an actual prefix. We're updating that prefix and you get a response. If we don't get a response, we should be able to do something useful. So I say set wait for ready false because it means that I have a fallback, I have a mitigation, that I can use some sort of default greeting, maybe yo, who knows, something universal, to set it instead. So I'll set wait for ready to false. So if that is unavailable, I'm not going to burn deadline waiting for it. I'm going to set it and move on. So do the same allocation request response, step 2. Step 3, invoke the service. So on that step, let gRPC take over that for me. And I'll sit there and wait for the status. So we've color-coded again, not for the way the language works, but to show you what parts of the service we're talking about when we look at this. Then you get your call status comes back, you check it, and you handle what's happened. If I'm the translator front end and I'm talking to my backends, the best thing I can do is actually propagate that deadline from the greeter on down the stack. So it creates its own client context, but this time it's going to do a copy. So we'll do the same way, but we're going to take the greeter context and take all the context about that RPC that we have, including that deadline, and propagate it down the stack. The only thing that isn't copied over is that wait for ready, because that's something that each serving component is going to have to decide for itself. Is that backend that I'm going to talk to, which is that translation DB, is it critical for me to actually give a response back to the greeter? For right now, we're going to say it's not, so the translator should be able to do something with one of its backends. Or we'll say, actually, if it doesn't come back, we have some other mitigation we can do. So I'll set wait for ready false again. And that's deliberate. You have to make that decision each time, and you should be making an informed decision about that. And then I do my usual wait. We allocate it, we invoke, and then we wait for the response to come back. So what does that look like when you take the whole code and you then fit it in? So the left-hand side is what we had before. We just replace that line with these steps. And that's how we're building reliability into it. So it's simple, straightforward changes to make, but it actually makes the service a lot more reliable. So you'll see you see the deadline setting, you see the wait. And then on the translator, when the translator is talking to that translation DB backend, this is the same lines that we're going to change again. So this time we highlight it to show you that we're copying the greeter context over to pass down the deadline. And you have to make a small change lower down just because of the way C++ works. So all in all, relatively small changes and relatively simple. Configuration. So if you look over the gRPC site, you find lots of places where you talk about different types of configuration. The only place you're setting the deadline is in that client API. But there's other places where you can set configuration. So we have the proto from before, and we have something called a service config, which you can read about. There's going to be more functionality coming soon, but for right now, it's not actually hooked into anything. So the deadlines are set in the client API. Okay, service, if you own a service, you should be setting some expectations for people of what when you're going to come back with a useful response. So if you're like a database and you have an RPC service to say, you know what, that table, I don't need anymore, you can drop it. If that takes you an hour, let people know it takes you an hour. So they have some sort of expectation, say, if I haven't heard back after an hour, either that didn't happen, something got lost, or maybe I can resend or retry. So you can publish those parameters, but they're not hooked into anything yet. This is a reminder. This is kind of non-obvious, and you can set stuff up and it will work and run. But if you don't set a deadline, your request can wait forever. It's kind of exciting if you have a service that's slowly building up more and more requests, waiting for a backend that's not there. So deadlines, kind of what's our TLDR? You need to make informed decisions about setting the deadline. You need to think about that. In particular, if you have a wide range of behaviors on your service, like if some stuff can be super fast and some stuff is super slow. You can get edge cases as well. Most of the time here, we're dealing with the simpler cases. So these are, like we said, these are guidelines. Clients should wait until the result is no longer useful. So if it usually comes back in 20 milliseconds, that's great, but that shouldn't be your deadline. If you set it to 40 milliseconds, that's an improvement, but still, if you're willing to wait up to 200 milliseconds for this to come back, or like a minute, set it higher. The last thing you want to be doing is scrambling to adjust a deadline because something is failing and something is taking longer than expected. For the service, specify the longest deadline you can technically support. So think about it. How long does this take? How long would it take in the worst case? And have it in your mind and be thinking about that. If the backend is unavailable, don't wait for the deadline to pass. That's where we're doing that set wait for ready. So if all you're going to do after the deadline is passed is the same thing you would have done before you waited for the deadline, don't wait. Fail fast. Fail early. But what do we do instead? So we talked a little bit about mitigations, but we're going to have to do something else instead. The other thing to think about is degrading gracefully. So this is where don't guess. So I'm going to walk you through some of the ways of degrading gracefully. Some services degrade by falling on the floor. It's not a great way to go. You want to be thinking about what options and what alternatives, or what other ways you can protect your system. So now you have a greeter. You can find and send RPCs to the translator. You're setting a suitable deadline. You know whether your backends are critical or not. You can tolerate some failures in that translator. But how reliable is the greeter, and how do we make it more reliable? So we have to start thinking again about it. So this is like a list of questions I'm going to keep asking myself, and I suggest you ask yourselves as well when you look at your services. How many in-flight requests can my greeter service support? I need to start thinking about that, and I need to have a good answer, even if it's a rough rule of thumb to kind of work it out. There should be a degraded mode. There should be a point where I say, actually, I can't take any more, and you can send some signal back to whoever is sending requests to you. We should have a graded mode for cheaper processing, even if that's 503s or something. Make sure you do something. And don't forget to measure it, right? Don't forget to say you're in a degraded mode and see when you're in degraded mode. Like we said earlier, measured gets fixed, right? So bear it in mind. How much work is needed to fail a request? If you have to do a lot more work when a request fails than when a request is working, you're going to have a bad time. Typically, it's when the service is under stress that you're going to start failing more things. So you need to have something cheap and fast that you can do when you want to fail. So if an error is more expensive, you have to start thinking about that and think about how your service fails. How much health does your service need to do something useful? Health. So we talk a lot about system being up and being healthy. And then it can be slightly confusing to say, well, what is healthy for my service? I run global ad serving systems, and I can tell you most of the time, there's parts of it that are definitely not healthy, and I would not like to send traffic there. Or parts of it that are kind of healthy. Or maybe you have a machine somewhere that's gone bad. And all the time, the service and systems have to be reliable enough. So if your version of health is that everything must be functioning completely perfectly and be responding within 200 milliseconds, you're never going to reach that. And you need to start thinking about how to manage that. Can a user get a useful request if some or all of the system backends are down? You want to be able to say yes to this question, and you want to be thinking about how you can do that. And you can make changes to the system design, like how the architecture fits together, or you can make changes in the code. And we suggest you think about doing both. But you need to sit down and think, what happens if all of my backends, all translator front ends, are down globally and not likely to come back for the next hour? Can I still do something useful for my users? And one of the last ones to bear in mind is, how does the server behave under heavy load? So typically, we're looking at services when they're behaving well and everything is fine and they're in a steady state and everything is useful. We need to figure out where your resource limits you hit first are. And that could be file descriptors. That could be something you're not expecting. And until you gather data, you're still guessing. So we say, degrade gracefully and don't guess. So as before, the gRPC library takes care of the communication, so the marshalling on marshalling, that deadline enforcement we showed you. This is another way to kind of build in some more reliability. So if we look at the translator and say, whoops, some of its backends go bad, maybe it goes bad. What can we do to make it work better? So one of the things that gRPC allows you to do is set and look for early expiry. So we're back to fail fast. If the greeter context has already told you, I have no more deadline, I have moved on, you do not want to be doing a lot of heavy processing work as the translator. And if it's an extremely short deadline, you're not going to do that really expensive long callout that takes a long amount of time. Send back partial results. So in order to do this, we're going to have a quick look, see how much is left, set a threshold for what that is, and do something useful. If I'm the greeter, there's things I can do to actually improve things as well. So we take the first step and second step as normal. The third step for setting the deadlines, and then invoking the method on the stub, as before, sending a translator. Then do something by default. So if it works, great, move on. If it doesn't work, do something cheap, and be cheap. Like, think about it, how to make it fast and work well. One of the things we suggest is you're probably going to want to log something. If you're logging on every error to an external system, or you're logging yourself on every error, and you have to wait till you log before you say something, are you going to log and say, all these thousands of options have failed? Like, make it cheap, whatever it is. And this is an option. There's a link there to glog, which is one of the ways to do this, log on every n. So you take a sampling of what's actually going on, and you know how many times it's failed. Well, you're doing that before you're sending that response. So make sure that's cheap and fast. So what does that look like when we actually switch that over? It's that simple. So we've taken a couple of lines and changed them, doing some logging so we measure and know when it's happened. What about healthy? Hi, Gabe.
Can I ask you a question?
Yes.
Hi, Grainne. What's hello in Irish?
So what just happened? Okay, gRPC has a way of you saying, are you healthy? But global services are never always healthy. So if you have to send an RPC to then send your RPC with your request, so if you're doing inline health checking, this is what can happen. And it's not a useful request to send. Okay, send the request and see what happens. You have mitigations in place and you can handle it. So health is a misnomer and it's underspecified. It means what it means to you, and you need to think about how it might be useful. It is useful in circumstances where you have a system that needs global state. It's not useful in a situation where you're kind of doing this inline. If you're doing this inline, this is what we suggest. If it's a critical backend, wait for it. If it's not a critical backend, move on and do something useful that's not available. You also need to think about the service moving as a whole. So it's never in this steady state of working properly all the time, and it will change state. So on startup, to help with this, are you healthy or not, is don't accept requests until you have a useful way of responding. If you have bad configuration or something is wrong, don't accept that initial client setting up that channel. Because all you're going to do is maybe send back something that could be actually dangerous or completely bad. On serving, don't die. It's the best thing you can do for everyone trying to talk to you. There's no system when it's under load behaves better if more of the service disappears and you put more and more load on the other. So you should be able to accept about 2x your normal requests on it, and even if that's in a degraded way. And the greeter component might not be healthy, and it might decide, maybe I shouldn't be around, maybe I should die. But if every greeter component everywhere globally decides to die at the same time, you've gone from a situation where you had maybe not great responses to no responses at all. So you want to watch out for that as well. On shutdown, finish accepting requests and then wait for that deadline to pass. So this is where you need to be thinking about what deadline you're setting for your services. So give it time to finish out and then close down. So quick run through. Load test it, measure it, know how much you can set. Have a degraded mode. In some way be able to say lower quality or cheaper. When everything returns an error, fail fast and be cheap. Know your critical dependencies, super important. Look at mitigating the ones you can. Anything that's critical that's left is functionally critical. You need to be able to do something useful about them, but know what they are.
So, measure all the things. This has come up during the days. I am particularly fond of the phrasing that Bruno had in the very first talk on Monday morning. What gets measured gets fixed. It's fantastic. Generally, in our measuring, in our monitoring, we want to answer these questions. What is happening? Why is it happening? Who made it happen? And will it keep happening? Starting with what happened, or what's happening. There's two kinds of things we want to measure. We want to measure server things, and we want to measure service things. The server things are the coarse metrics, but they are absolute. So your CPU, your memory, your network, your disk I/O, these are the cost to run your service. On the one hand, you need this to feed your capacity planning and your alerting. When you're out of these, that server is basically done. So at that point, that server is failing quite badly. They have limits. You need to know them. You need to watch them over time. This is your planning. Additionally, for your server things, there is the easily forgotten startup time. That is the time to recovery it takes after you have fixed the problem. Track that over time. It has a tendency of creeping up over time. It has an unfortunate tendency of not getting less over time. Watch that, manage that. This is an additional time that you're down after fixing whatever big problem you had. On the service side, the service things, these are the bigger picture. Your request rate, that's your denominator. This is what you use to scale your service. This is how you identify your SLA. This is how you identify your SLO. That's your denominator. Of course, you need to know how many queries you're getting in the first place. Otherwise, you don't know what's happening. Your success rate, that's obviously the numerator of your most important SLO, are the requests actually working? Interestingly, there's usually one way to succeed, but there are many ways to fail. Track failures by type. In HTTP terms, a 404 not found is a very different kind of failure to a 500 of some description. Your latency, fast is better than slow usually. Track this over time. It has a tendency as well of creeping up over time as your service matures. If you're running hotter and closer to your limit, be aware of this. And of course, if it gets too high, you might want to alert yourself. A frequently forgotten one at the service level, at the server level, Ronnie mentioned it with the maybe log every n. Not just for error, be aware of your logging behavior. If you log your requests, are you doing that synchronously? If you're doing it asynchronously, what happens if your log buffer is full? Does it then suddenly turn synchronous? Be aware of what you're doing. Be aware of how many things you're logging per second, per request. Is that expensive? Eventually, even disk space gets expensive. So, measure the server. We depart from our C++ example to an example in Go because it's the easiest one. In combination with Go and Prometheus. Prometheus, for those who have never heard the term, it's an open source monitoring system. They provided or somebody, I don't know whether it's from the Prometheus project itself, provided a third-party library that just hooks into the gRPC library. Those two lines in the middle, the interceptor, that's all you add to your normal Go boilerplate of setting up your server, and suddenly you have all of the metrics exported, and Prometheus has them. If this is how you monitor your server, but of course, if your server gets the RPC and sends a response, if your client never hears of that, does anybody care about the server? Measure the client as well. In Go, it's just as easy if you're still using Prometheus. Those two lines in the middle, they're basically identical, except it's called a client interceptor instead of a server interceptor. That's how easy it is. You get all of the data. In the other languages we have, you're a bit more on your own. There are similar facilities available, but nobody has yet written that kind of convenient library. Why is it happening? Well, let's stick to our latency example because it's the shortest code example. We'll go with the latency measuring. Latency is easy. It's sort of the time at the end minus the time of the start. That's how long it took, right? So you save the before state in normal C library calls, trivial code. You do whatever it is you're doing. In this case, we send the request and call the backend. Again, with the color coding. Ooh, look, I have a laser. Somewhere. And then when it comes back, you check the end. Again, normal C library code, get the time, subtract the now from the start, and then log it to your favorite monitoring system saying what it is that took this time. This is still more or less of a what is happening. Now the question is, why is it happening? The answer is as easy as the question. You took as long as you did because you did the things that you did. In this case, we called the backend. Well, that's probably where most of the time went. So surround that code with the exact same thing. This is just before we called the backend, then we actually called the backend, this is just after. And that way we know from the client's perspective how long it took and how much of that time were we waiting. In code context, take the time at the start, take the time right at the end. The highlights are amazing. And surround just your call with the time. Export these to your favorite monitoring system, whatever it is you're using, and you know something about why it's happening. Why is my service behaving the way it is? The next thing you want to know is who made my service behave the way it is. There are multiple answers to who. There's the authenticated user. If you're using any kind of login system or like TLS authentication, you've got another certificate, whatever it is, you've got the authenticated user. But you also probably want to know which particular service called you. Who was that client? Maybe this was the QA environment, in which case the errors are not that interesting. On the other hand, you may also want to know the calling site. So maybe the code is different. Maybe there's a particularly expensive query that you wish to attribute all the way up the stack. What change made that happen? Why is this happening? Who did that? In gRPC terms, the easiest way is to use the arbitrary metadata facility. Just when you make a call, say, here's something you want to know, key, value. Arbitrary strings, you can add as many as you like, and they can be as big as you like, but remember they get transported, so maybe don't add all of them at massive sizes. On the server side, to read them, well, the bolded lines, again, you just ask what was the client metadata. You can have the same key multiple times, so it's a multi-map in C++ terms. Other languages have slightly different names. Find the key, find the value, do whatever it is you want to do with it. There's a similar facility the other way around to provide a bit more information about what's going on. In gRPC, you get two types of metadata, initial and trailing, where you may want to say, here's your translation, but this was, the status is okay, but I was offline, so maybe I didn't use Google Translate, only my database. Google is working on open sourcing the census infrastructure, which adds all of that stuff automatically to gRPC calls. The library code is there if you want to look at the C implementation, but that is really dense. It makes my brain hurt. So I recommend waiting for the public APIs to turn up. We expect to be expanding on this a bit in the future talk, so that slide will change significantly by having no code. This happens, it's great. Not yet. Okay, now we've measured stuff. We use these metrics for all sorts of things, you know, for capacity planning, for your SLA negotiations, for your troubleshooting, for alerting, obviously. What do we do with that data? Here are some data sets. They're great. Obviously, we don't like dealing with that. We use your favorite number crunching tool. It's whatever. It's a spreadsheet, or it's your monitoring system, or something to manipulate the data, to summarize it. Here are some frequent summary statistics that you might want to run over data. You take means. You take variances. Everybody always loves a linear regression, or line of best fit. In this example, that last one looks particularly great. So all of these are almost the same for all 4 of those data sets I showed. That linear regression, that's great. That's a growth formula, right? Right? Well, graph your data. Humans are really great at spotting patterns, even if there's no pattern. Computers are really great at spotting patterns they have been taught to spot. They are completely incapable of identifying that, hey, actually, maybe there's linear regression here. I can do the math, and the math does not lie, but it doesn't actually answer the question I had. Graph your data. Measure all the important things. You want to answer what is happening. Gather your server metrics as well as your service metrics. Break them out by type. Different failures have different reasons, need different responses. Why is it happening? Group your backend metrics with your incoming metrics. This is a fancy way of saying, remember that you're a stack. Trace the stack, be aware of what is happening down the stack. Who made it happen? Again, group your metrics by the caller, by the user, or by the calling service, by the calling site, whatever that is. You probably don't want to keep a big cross-product table in memory. Feed your logging system with this data so that you can analyze this after the fact. Once you've dropped the data, once the data is gone, it's gone. Log it for post-processing. Once you have that, the question is, will it keep happening? And the answer is always, well, maybe. So this is where you can use your favorite machine learning system or just, you know, linear regression if you've graphed it. Do a scatter plot. Look at maybe whether there is something that might make sense. Then try to make a computer find that sense.
So now we're in the final part of the talk, and this is our rapid fire round. So gRPC isn't going to solve all your service problems. It's not a magic bullet. It doesn't fix everything for you. But here are some of the top 3 answers that are given for this is how you fix your service, which you should question and think about. So frequently given answers.
Quality of service makes the important things go faster. Caching will make it faster. Okay, it's not going to take longer than X, whatever.
And here are some frequently missing questions.
Oh, really?
You should definitely be asking that question and then looking for data and some ways of verifying that these things are actually true.
So here's your quality of service makes it faster, where you have like the fast queue and the slow queue. I don't know, maybe like that looks like a problem. It certainly looks like a problem to me, but on the other hand, maybe it's not a problem. Right? Maybe that one person there has a special request that will take forever to deal with, and that fast queue, that's just one burst of cheap to process requests. Like in this example, maybe that's a bus arriving, they've got a group ticket, right? So whoop, in they go. Measure, otherwise you won't know. Frequently people use, so you have your reservation maybe. Your QoS suddenly means that you've got unused capacity. You're throttling your batch, but your online transaction isn't using that. Common answer, especially in the network world, is profiles. The network, it's a bit easier because a packet is a packet, and maybe more important, but isn't slower. You can use the sharing, that's great, so unused capacity gets used by whatever traffic you happen to have. The red line there is a suggestion or a profile or a guideline, but not a hard limit. But on the other hand, maybe on the left-hand side there, you've now scheduled all of those batch requests, you're processing those batch requests, and now you've got some, small, fast, high-value requests coming in, and they're queued behind that. Maybe this makes sense, maybe it doesn't.
So caching makes it faster. So your old problem was your service was slow. So you add caching. Now your new problem, Cache expiry. What do you do about that? And when do you do it? Other new problem, cache revalidation. Still a problem, and hasn't been solved by your caching, is negative caching. So if you don't get an answer, what do you do?
It won't take longer than X. Well, again, maybe.
Does it have an SLO?
Does it have deadlines?
All the way down the stack.
Do you understand your dependencies?
I really do. This is one of the things we often forget.
There are hidden dependencies. You're calling all sorts of libraries. What happens if your DNS goes away or is slow? Like, I don't know what happens. Do you know what happens? What happens if your log buffer is full? I mentioned that. So do you suddenly block because you can't log what's happening?
And what's your mitigations? Like, is it a human getting paid to run really quickly and answer it? Like, it won't take longer than the 5 minutes it takes them to get to a computer and fix it? Or have you thought about how to automate some of this and take it away so that the human can come and debug? Because we're good at looking at the graphs. Computers are good at lining them up for us. That stuff it isn't.
Quality of service may make the well-behaved important things go faster.
But it needs to be managed, right? You need to be thinking about it.
And caching may make it faster.
And it can also make everything more complicated and maybe less correct.
And it maybe won't take longer than some amount of time.
So we set our deadlines, and our deadlines are enforced by gRPC, but not everything is within that stack. Like, you could be doing processing that's happening outside that. How long is that going to take? So we kind of say they're guidelines, and we kind of went through 6 different areas we talked about. But you should be thinking about these and figuring out how to answer these questions or what kind of questions you need to ask for your service. So we kind of reduced it all down to TLD or be a good Jenga block. You are one part of the stack, and the stacks are global and large. And you want to be well behaved. You want to help out the people sending you stuff, and you want to have good behavior on the people you're sending things to. So what next? We'd love to get your feedback. We'd love to hear what you like and don't like. We'd love to hear what you'd like to see next. So you can go to the GitHub. The link's already there. We'll be sharing the slides so you can see this. That's great, but you still got questions. So we're going to pop up again at SREcon and EMEA. And also, you're going to see more examples pop up on the gRPC actual website. So we'll be showing more things there and explaining more of the features as they become available.